What is a buffer? A buffer is a solution that resists pH change. So buffer now we say it resists pH change, it doesn't mean it won't change. It just will change a little bit as long as it's still a functional buffer. The only time it will go crazy is when you break the buffer and it no longer works correctly, which you will see on your lab as well. You should have seen that. I'm trying. All right. All right, so we want to talk about how we can make a buffer. There's the basic idea is to make a buffer, you need two components. You need a conjugate pair, okay? So you need a conjugate pair. So this is a pair here. Basically, they're the same ion component. If you use acetate, the other thing has to have some sort of acetate in it too. And they have to be a conjugate pair. Okay, so an example is acetic acid. An acetate ion. Acetate. So H2C2, not H2C2. HC2H3O2 versus C2H3O2 negative ion. Now, because we cannot get this ion to be by itself, it has to exist with a spectator ion, which in this case we always use sodium, and basically any group 1, because those are strong bases if you form it, and they'll be really easy to pair because they're neutral. So example here. We wrote this one down, right? So weak acid part, and we pair it with a conjugate base, which really, not just the conjugate base ion, is really the salt of it, because it's an ionic compound. Salt of conjugate base. So in this case, if we want to use acetic acid, we would take acetic acid, and then we pair it with sodium, C2H3O2, because this is just a spectator ion. Okay, so we need a conjugate pair. They both have to have the same ion component. So C2H3O2, C2H3O2, that's one example. Now this is if you have a weak acid and a conjugate base. What if you had a weak base? Can you still make a buffer? Yes. We have a weak base. We have to pair it with the conjugate acid. And really, it's the salt of the conjugate acid. Okay, so example, weak base ammonia. What's the ion that comes with it? Ammonium, NH4 positive, right? So I'm going to pair it with spectator ion. I'm going to use Cl. And this one here, spectator ion, because we know Cl is neutral also. Because it was paired with HCl, came from a strong acid. This has no acidic or basic properties. Completely neutral, just spectator ion. So like neutral. All right. So that's one straight, direct way to make it. Pour some acetic acid, pour some acetate in there. So sodium acetate could be used, or we could use ammonia, ammonium chloride, make a buffer that way. Now, an alternative way to make it is if you don't have some of the stuff handy. I can show you how we can make it. Alternative way to make a buffer. We use a weak acid and a strong base. Now this was an example you use in your lab. You use a weak acid unknown and you pair it with sodium hydroxide, which is a strong base. So I'll write down in brackets. Sodium hydroxide is a good example. So how does that work? You don't have your conjugate base here, but you have your weak acid. So if you start off with just the acid, and then you pair it with sodium hydroxide, I'm not going to write the sodium here because it's spectator. I'm just going to write the hydroxide, okay? So in this case here, OH negative, okay? And then that and that will see each other and they will start to react. So hydroxide is going to find the H that falls off from the C2H2O2, and you're going to make water. And then what's left over is the ion C2H3O2 negative. Now, if sodium was here, sodium will be paired here, and sodium will be paired with this guy. So it's just a spectator ion there. Okay? So in this case here, even though you don't have the conjugate base, you can use sodium hydroxide, strong base, to force them to make some self-sacrifice this guy to make some of this conjugate base. So in the end, you still have a weak acid and your conjugate base. You make it indirectly, okay? But it takes the sacrifice of this guy. This is the y over 20 minus y equation thing, okay? Where if you had 20 mils of acid and you put 1 mil of sodium hydroxide, then there will be 19 of this left, none of this because they all reacted, and then you'll have 1 mil of that. So it's just self-sacrificing your weak acid by reacting with sodium hydroxide, and you will indirectly make some conjugate base. Then you have a buffer, okay? So another option is if you use a weak base and pair it with a strong acid. So an example of strong acid, we'll use hydrochloric acid. It's pretty common. So if you have ammonia plus HCl, right? And well, I'm not going to write it. And we'll do that. We'll do this the full one, and I'll do this spectrum, the net ionic later. So this is NH4Cl here. Okay? Now, if you're really looking for the base, it's this guy. Base plus the H plus from the acid, okay, from the HCl, and then you're making ammonia. So, and again, Cl here is a spectator ion. Okay? So yeah, you can make make buffers using 2 different ways. The most common way is actually to mix the acid and the conjugate base, or base and the conjugate acid right away. If you don't have the conjugates, you can actually use the weak stuff, pair it with this or strong base or strong acid, and you can actually create a buffer situation. In this case here, you're self-sacrificing the weak acid, or in this case, you're sacrificing some of the weak base. All right, so we want to learn how to calculate buffer pH now, okay? As you can see, we did use a formula, but you actually can use an ice table, but it's a lot longer. So I'm going to show you the ice table just to show you how it's linked to the previous chapter. But then you don't have to use the ice table because our questions here will be simplified enough where you can use a shortcut. And when you can use a shortcut, you will actually use the equation. Calculate pH of a solution made of 0.1 HC2H3O2 and 0.1 the salt of the conjugate base. Okay, and then they give you the Ka. 1.8 times 10 to the minus 5. So traditionally, if you were to do an ice table, well, you would just write, well, I have a weak acid. I'm going to go ahead and write the equation for the acid here, okay? So this is a buffer making from an acid. So you have HC2H3O2, and then water. and your ions. All right, so you have HC2H3O2. Oh yeah, and then we got Ka. Ka is that over that. C2H3O2 over H3O plus divided by HC2H3O2. Okay? And that we know equals to 1.8 10 to the minus 5. It's given in the question here because they gave us a Ka, right? So we're going to go ahead and set up the ice table. Now initially I have this much acid, so 0.1 goes here. And you don't have any hydronium, but they did put in some acetate ion. So you also have 0.1 of acetate ion. None for this hydronium. Okay, and then the change will be, we go towards the side with a 0, so this is plus, and that side is the same as that. So both of the products will be plus, the reactant will be minus, and it's 1x each time. Okay, so you have 0.1 minus x, 0.1 plus x, and then 0. So we will be using our shortcut because this number is small. So we can go ahead and cross this x out and cross this x out. See how it used to be all negative, minus, minus. Now it's like some of them is plus, some of them is minus, okay? So we're going to put all that in here, Ka, in terms of x. So it's 0.1 plus x. I'll cross the x off. And then 0, not 0, x. 0 plus x is x, not 0. Right here. 0 plus x is x. And then there's your x here. And then you go on the bottom, 0.1 minus x. And then that x crosses off. Both of them cross off. And that means 0.1 and 0.1 also cancel off, right? X equals to 1.8 times 10 to the minus 5. So once you get that, we can do the check step, and you can see it's the slowest, smallest step. So you don't really have to do this. In fact, you don't even use an ice table here, but I'm going to show you how it's actually related to the previous chapter. So a check step, 1.8 times 10 to the minus 5, take your x, right? Compare to the original, 0.1, and then you hope it's less than 5%. So you take 100 times 100 to get a percentage. You get 0.018%, which is really, really small. So your approximation is good. And then to get the pH, is minus log of H3O plus, which just goes right there. And x is 1.8 times 10 to the minus 5. So you can get your pH in this case is 4.74, right? So that's how you would do it if you use an ice table. Now the equation that they give you is called Henderson-Hasselbalch equation. So it's pH equals to pKa plus log of base over acid. Now this one is a lot faster, and I'll show you, you can get the same answer over here. So pH is what we're looking for. Do we know the pKa? Yeah, we know the Ka, it's given in the question. So pKa is minus log Ka, so I'll go ahead and write it down. And then plus log of base over acid. Well, what's my concentration of base? It was 0.1. Acid is 0.1 also, so we'll go here. So in this case here, you actually are comparing the ratio of base to acid. We're using molarity here because they didn't tell us the volume. Sometimes the molarity is safe, you can use the volume or really the mole ratio here, as long as you get a ratio of the base to the acid, okay? So in this case, we also still get our answer as around 4.7. So always use this equation. This equation, you probably want to memorize it. It's not, I don't think it's on the periodic table, but it's a really small equation. So just remember pH equals pKa plus log base over acid, okay? Now, we're going to talk about, before we do more calculations, I'm going to talk about how we can make good buffers. So as you notice, sometimes the buffers can break. Oh, another thing is when we want to make the buffer, we say we have the acid and the conjugate base. So this common ion effector will be a big thing when we go to the next chapter as well. So I just want to show you that common ion effect actually exists here as well. What it means is basically in the beginning, if you have just the acid and then just going, everybody was zero, it would go a certain direction. But if you added some base to it, which is what a buffer is, this presence of this base actually will shift the reaction um, to the left here, because without the base, it was happy, and then you want to put some base and it will actually shift the equilibrium position. The molarity will say this one will go up, that one will come down. It pushes the shift to the right and shift to the left part. Okay, so we'll be learning this in the second part of this chapter here. So when you talk about how to calculate the pH and give you the formula, I want to show you what makes a good buffer. So the best buffer, okay, is when you have equal concentrations of acid and base, so 1-to-1 ratio. And the best buffer has the biggest amount of concentrations of acids and bases, because the more concentration you have, the bigger the line of defense they can have to work against the pH change. If you have very small, a little bit of buffer here, yeah, it still works, but it will break a lot easier. Okay, so you got to remember, equal concentrations is the best. The more the concentration is, the better it is. And if I gave you a list of acids here, when will an acid be effective? Basically, we talked about 1-to-1, that's the best. And then the ratio of the pH range is actually limited. Effective pH range is when you take the pKa and plus minus 1. So if I have like a pKa of 4.25, then my pH of the buffer that I can make is going to be from 3.25 up to 5.25, because it's from the pKa you count down 1 and count 1 up 1. Okay, this is when you can see how to make a good buffer. So we'll be trying that here. Now take a look at this one here. It says here, you want to make a buffer with pH 4.25. So you want to pick a pKa that's closest to 4.25, okay? Now, if the pKa is 1.95, you can make a buffer from 0.95 to 2.95. That will not reach 4.25, so this is out of the question. Now, the second one is actually possible because you can make from 2.34 up to 4.34, right? Yes, you could possibly make it with nitrous acid, but it's going to be on the brink of the last side of effectiveness. So the best buffer to choose is the one that's closest to 4.25. So in this case, pKa of 3.74 is the best because it's closest to 4.25, and the range is from 2.74 up to 4.74. If you looked at this acid here, 7.54, that's way too far off. This would be used to make a pH buffer that's a lot higher. Like it ranges from 6.54 to 8.54. Okay, so that's what we'll be having to learn. So let's go ahead and do more buffer calculations. And then change the page. All right. Calculate the pH of a solution formed by mixing 250 mils of 0.150 molarity NH4Cl and 100 mils of 0.2 molarity ammonia. Now, this question is a little bit different from the one we just had. We'll give you the kb of ammonia in this case, okay? Now, why is it different? Okay, so I want to take a look back at the first question and see the difference in wording there. Now, this question here, it says, the buffer solution is already pre-made, and this is the resulting molarity, okay? So that's why you use these numbers, you plug it in to the values in the equation or in the ICE table. In this case, you can't do that because they're giving you what's in the stock solution. I took 250 of this guy, I took 100 ml of this guy, and then I mixed them. So you have to recalculate the molarities here, okay? So you can calculate the moles first, and the volume total is 350. So basically take the moles divided by 350 to get the molarity. So really, the mole ratio is enough to get the ratio, true idea of the base versus the acid. So you also have to recognize that this is the base and that's the conjugate acid, okay? So the equation here is pH equals pKa plus log of base over acid. So basically you want to put the ammonia up here and then the ammonium down here, okay? So to do that, we can go ahead and get pKa. pKa is minus log of Ka, minus log of Ka, right? And then once you get pKa, so I'm going to go ahead and tell you Ka times Kw equals to, Ka times Kb equals to Kw, pKa plus pKb equals to 14. So we learned that in the previous chapter. We talked about it. And then pKa or pKb is minus log Ka, pKb is minus log Kb. Okay? So that's something we learned before this. I'm just rewriting so you have it here again. So we need the pKa, but they gave us the Kb. So you can go ahead. I like to do find the pKb and then subtract from 14. It's faster for me, less chances of error. Okay, so I'm going to go ahead and do that part, pKa, and then we'll do the ratio of base to acid, which means you have to calculate the moles first, put the moles in here, or you can do the molarity and put it in. And I'll show you that you get the same answers anyway. So let's do the pKa. So pKa is going to be 14 minus pKb. And then pKb is going to be minus log of Kb, which is given. 1.8 10 to the minus 5. And we get like 4.74 here. So that means pKa is 14 minus 4.74, and I get 9.26. So that's one term. So, you know, if you weren't careful, you just take minus log of whatever, you put 4.74 in your equation right here. That's wrong because they're asking for pKa. Okay, so now we want to do moles of the acid and the moles of the base. So we'll do ammonium because that's on the top, which is at first. Okay, so moles of ammonium is my acid component. And I have to take the volume times the molarity, but the volume has to be in liters, okay? So 0.2500 liter. And then molarity is moles per liter. Okay, so we're talking about the ammonium. That's why I wrote the number for ammonium right here. Chloride is just a spectator ion, and 1 mole of NH4Cl has 1 mole of NH4, so that's why I just wrote the molarity of NH4Cl here. So you get here in this case, you get 0.0375 moles of ammonium ion. You really get chloride ion too, but I'm not going to talk about a spectator ion here, okay? So if you wanted to do molarity, you take the molarity, you take the moles here, 0.0375 moles, and you have to divide it by the liter of the total volume, which is 350 mils, so turn into liter is 0.350. And you get the molarity of 0.107. Okay, now in this equation here, in the acid term, you can use the moles. If you want to use the moles, you can use the molarity too, it doesn't matter. For me, it's faster to use moles because you skip this one extra step here. But you have to make sure, the reason why we can skip this step is because the molarity of the next guy is also take the mole divided by 0.3500. So the ratio of that is going to be the same. So let's do the moles of base here. Ammonia is our big weak base. You take 0.1 liter, this is 100 mils, and then you multiply with the molarity that's given, 0.2. And I get 0.0200 moles of NH3. And if I want to get the molarity of that guy, take that moles divided by 0.35. You get 0.571 NH3. Okay, now let's plug it all back in. pH equals to pKa plus log of base over acid. Now I promise you, even if you use molarity or moles and moles, you get the same answer. So I'm going to show you that here, okay? So you can do pH equals to 9.26 because we just calculated up there, plus log of, I'm going to do the moles first. Base is 0.02, 0.0375, okay? You get an answer here of 8.98. Now if you do the pH of 9.26 log of 0.571, 0.107, you get 8.98 as well. Because the ratio of this guy and that guy, you can cross it off, and then you still have the same ratio of the moles. That's why it's the same answer. Okay, both of them will give you the same answer. So as long as you get some sort of ratio of base to acid, you're good. Whether you use volume, you use molarity, depending on the situation. In this case, we can just use moles. Or you can stick to molarity. Okay? If there are no questions, let's do some more. What is the pH of a buffer? Or sometimes you won't even call it buffer, just say solution. Prepared by 10.70 grams NH4Cl and 20 mils. 20 mils of 12 molarity NH3 and enough water to make 1 liter of solution. Do you need the previous page? All right, I'll flip it over for you guys to keep writing. Let me know when you're ready and I go back to that question, okay? Like, did you want the top part? Because you're looking at the ratio. The last question here, this one here, why moles and molarity work. Can you guys see the top? Are you guys done with the top part? So I can show the bottom part here. So the ratio you care about is the base to the acid, right? So I'm gonna write it out for you. Okay. Hopefully you guys are done. If not, let me know. Actually, I can zoom out for you a little bit, maybe. Anyway, so I'm gonna write on the bottom here. This number here, why is it the same as that, okay? So the ratio of 0.02 to 0.0375, right? That's the mole ratio, correct? Now, why is it the same as the other guy? Because the molarity ratio is 0.02 over 0.3500. And then the next one is 0.0375 over 0.3500. That's why I say you can cross, if you cross that part out, that cancels off. And the ratio becomes just a mole ratio. So that's why you can use either moles or molarity. For me, I like to try to save time. If you're on a test and you got the mole ratio already, you don't necessarily need that extra molarity term in there because it'll give the same answer because these two cross off. The volume, the total volume is the same for both of them. Okay, are you guys done with this question? You need me to move it a little bit more? Okay, I assume you guys are done writing. And then I'm gonna go ahead and turn the page, okay? Now, this page here, you can take your time to write this question down. I can explain to you, I mean, it's literally the same question as before. The only thing is they didn't give you the molarity, they gave you grams this time. So you have to find a molar mass, okay? So on the test, I like to try to give out molar mass when I can, otherwise you have to count from the periodic table. So you need a molar mass of NH4Cl. So it's 53.491. And then you also need a Kb of your base. Okay, so now our goal is, again, we have to find the pKa, and then we have to find the ratio of base to acid. So we have the system here. So equation, I write it again, pH equals pKa plus the base of acid. All right, so first thing we want to do is go ahead and find the pKa like we did earlier. Actually, isn't this the same pKa because it's the same system? So I'm just gonna copy over. It's like 956. You guys remember that? Like this page here, we just did that. Literally the same thing, right? We get the pKa is 14 minus pKb minus log of kb is that, and that's how we get a pKa. Okay? So it's the same exact thing. I'm just copy 9.26 over. Okay? Because you see how this is for ammonia too. So makes my life a little easier. Look at previous page to get this is 9.26. Okay, so we'll make a note here when you're studying. Refer to previous problem. That way you remember, oh, how in the world did I get that 9.26? It's actually, we just did that like a few minutes ago. All right, so we want to focus on base and acid. Okay, so I would say get the moles of ammonium. And I know my total volume is 1. So really in this case here, molarity and moles will have the same number. Okay, so I'm going to focus on getting moles of ammonium and moles of ammonia. So let's go ahead and do that first. It is 10.70 grams of ammonium chloride, and then 1 mole of it weighs 53.491. And we know that 1 mole of ammonium, I'll write it out, 1 mole of ammonium can be found in 1 mole of ammonium chloride. Okay, so that contains over here. Ran out of space there. All right, so now we know the moles of ammonium. Let's see, it is 0.2 moles of ammonia. If we put it in 1 liter, the molarity is the same number, right? And then I'm going to do the next one, which is going to be my ammonia. Get the moles of ammonia now. Is to take the volume in liters times the molarity. So I'll go ahead and show you how I did the turn into liter. 1 liter is 1,000. And then the molarity is 12 moles over 1 liter. You get 0.24 moles. And then the molarity of that guy is 0.24 moles over 1 liter. You get the same number. Okay, so in this case, whether you use the molarity, you cancel the one, or the molarity answer is the same as the moles anyway, because it's 1 liter. But if it's not the same 1 liter, you get 0.35 like earlier. That still crosses off. So you could have just stopped at the moles. In this case, it's literally the same number. It doesn't matter. Okay, so I'm going to go ahead and plug it up here. pH equals 9.26 plus log of base. So this is my base, okay? Base, and then acid. Moles and molarity are the same number, so it doesn't matter. So it's going to be base is 0.24 over 0.2. And I get 9.33. Okay, so now we're going to do a little bit different. Instead of just calculating pH, they're going to give you the pH, and you find the ratio of your base and acid that you need to have. Okay? Everyone good here? Okay. I'm going to turn the page. If you're not ready, let me know. Okay. To make a buffer, pH 4.25. This is related to the question we just saw on the slide. Formic acid is chosen. Excuse me. All right, formic acid is chosen. The pKa for this guy was like really close to 4.25. Well, not really close, but closest among that list. Find base over acid ratio needed for this buffer. Did you guys notice if your base and acid ratio is 1:1, your pH equals to the pKa? Well, in this case, the pH and the pKa are different, right? So the base and acid ratio is not going to be 1:1. The last time we used log in the last equation, this time we don't. The question is finding this ratio. They're not asking you to find the log of the ratio. The equation is still the same. But the equation is still the same. You get this. See that? But they're asking you to find just this number. They don't care about the log. They want you to find that. So you still have it. My last question, I didn't write log, unless I've forgotten it. Yeah, I forgot to write the log. I wrote the log up here, and then I forgot to write this down here. Yeah, good catch. So the equation never changes, okay? We always have the log. And don't use natural log. We are using the base 10 here. 10, log 10. So there is a log here. Make sure you guys add that to your notes. So now we want to go back over here. We use the same equation again, and this time they're asking for this. So before this, we were looking for pH, right? And we had to solve for this and this and put it together and get pH. Now they gave you the pH, they gave you the pKa. Your job is to find this little ratio here, okay? So I'm going to go ahead and plug it in. So you need this number here. So we'll go ahead and start working your algebra. You take minus 3.74, so you get 4.25 minus 3.74 equals to log of the base over acid. Okay, so now we get 0.51 over here, and you still have your log base over acid. Now we want to get rid of the log term here. We take 10 to the power on the bottom. Now, is there a negative here? No, don't put a negative here for fun. It doesn't belong there, okay? So sometimes your equation is 10 to the power negative pH, is find the H, but we're not looking for that here. This just how happens that we are using log in the equation. We take 10 to the power off that number here, and this number is a positive number. Do not add a negative just because you memorized it in a different formula, okay? So you have 10 to the power 0.51 equals the base of acid ratio, and that's all you're looking for. So the ratio of base to acid is literally just 10 to the power of 0.51. You get 3.24 as the ratio. That means if you have 1 mil of acid, you must have 3.24 mils of base. If you have 10 mils of acid, you must have 32.4 mils of base. That's the ratio. Okay? Everyone good here so far? Okay. So I'm going to keep going. If you guys are done writing, let me know if you still need some time. We want to talk about how buffers work by self-sacrifice. I'm going to write it out, but you probably have seen this if you were doing the lab. Let's go ahead and write it out in our notebook this time. The way a buffer works. To resist the pH change. To resist pH change. Okay, number one, when we add a strong acid. So it's already a buffer, and you go ahead and you pour some HCl in there. You pour strong acid to the buffer. Okay, if you put an acid in, a strong acid, the base component of the buffer, so the basic component, the base part, of the buffer will self-sacrifice. It goes to work to resist pH change. So this is where if you added HCl, and really you're focused on adding the H, you take that H and then you have it react with the basic component of your buffer. So we were using acetic acid buffer here. We'll just say, we'll use an example, okay? The buffer, maybe our buffer is HC2H3, O2, and C2H3, O2 negative. This is one example of a buffer we could be using. So you would take this H and plus the basic component, which is that one, and then you just turn it to a little bit more weak acid. So you take incoming strong acid, it's neutralized by some of your weak base component, weak base component of your buffer. So these two go down. Like if you have 1 mil in, this 1 mil of it sacrifices to make 1 mil of this, because it's 1 to 1 to 1 ratio right now. So you will have the weak acid component. So it doesn't really change the pH here, because the pH depends on what? pH equals to pKa plus log of base over acid. So if you have the situation here, all that happened when you add the incoming H is you change the ratio of the acid and base a little bit. Acid would have gone up a little bit, but how much base went down? How much base went down depends on how much acid you poured in. So the ratio tweaked a little bit. Because it tweaks just a little bit, the pH, it won't change a lot. Your pH will decrease just a little bit. Okay. Now, if you did the opposite, then we'll have the opposite effect. So I'm gonna go ahead and write down. It decreased just a little bit. It doesn't really change. It doesn't have a big change, big pH change, because acid went up, the weak acid, and then the weak base went down. So the ratio changed a little bit. If we we put a strong base in, let's see what happens. If you put a strong base in, the acidic component of the buffer self-sacrifices. So when we add a strong base, so like sodium hydroxide, to the buffer, the acidic component self-sacrifices. Hey Maria, I think you missed our time change. We shifted forward this Sunday. So if you're not in the country, we changed our time. Make sure you watch the previous parts of the video. All right, it works to resist pH change. So if we add NaOH, we're really concerned with the OH that you're adding in. So OH is going to run into your acid, which is HC2H3O2. And then you can make some water, HMOH. And then you'll have some weak base being formed. So this is kind of similar to the indirect way of making a buffer, right? But we already have a buffer. We're just saying what happens if you add a strong base to the buffer. So what happens is, well, the weak acid goes down because you have to neutralize OH, and the base part goes up a little. So we'll change your ratio a little bit. But the pH won't really change because all the OH that came in was neutralized with this guy. So again, pH doesn't change, it just increases a little bit. Because I spelled it wrong. Base this time goes up, the weak base, and the weak acid goes down this time. So all it does is change the ratio a little bit. This part changes a little bit. Okay? All right. So everyone good with this? We can continue some more. So now we were saying how, yeah, we can tell it's going to go up a little bit, go down a little bit, but we haven't done any math yet. So I want to show you, you can actually calculate exactly how much it will go up and go down. Okay? So let's go on to the next page. If you guys are ready writing, I'll finish with it. A few more seconds in case you haven't finished. Let's see. All right, so I'm gonna go to the next page and write the new question here. A 1.0 liter buffer contains 0.100 moles of HC2H3O2 and 0.100 moles of NaC2H3O2. Ka of HC2H3O2 is 1.8 times 10 to the minus 5. Okay, so notice this 0.1 and 0.1. So pH and pKa is the same value here, okay? I'll write it down. The reason why it's the same, because log of base or acid, when you have log of 1, you get 0. So pH is then at the point equals pKa. So pH equals to pKa plus log of base over acid. So for this buffer here, if this is 1 to 1, log of 1 is 0, so this term disappears. That's what pH will be the same number as pKa. How did you get pKa? Minus log of this guy. Minus log of the K, okay? So the question is, once you know you have this buffer, calculate the new pH after adding 0.010 moles of NaOH solid to the buffer. So they just drop a few pellets basically. And then it says, after you do that calculation, compare this pH to when we add 0.010 moles NaOH to water. So we know if you add a strong base to a buffer, the pH will go up a little bit. Not a lot, just a little bit. We also know the equations it uses to work, right? What's the equation? It was OH from sodium hydroxide plus the weak acid component, which is acetic acid. And then you make water and you make acetate. And we talked about, we know if you put one of this will sacrifice and you make one of this. So I'm going to go ahead and do a little bit of a table. So before OH addition, and then we find out how much we added. Okay, and then we find out what's left over, so after addition. After you add it, the values of the base and acid here will go into this part, so you can calculate the new pH after you add it, so part A. So before we added OH, there was no OH in the system. There was 0.1 mole of acid, and there was also 0.1 moles of your base. We don't count water because water is liquid. Now, how much NaOH do we add? We add 0.01. So we are adding 0.01 moles over here. So basically, this one has to sacrifice 0.01 moles to react with the 0.01 moles that's incoming. So this one goes back to 0, right? They neutralize it all. But this one here now is 0.1 moles. You sacrifice some, so you have to minus how much did you sacrifice? The same amount of OH that you had to neutralize. So minus 0.010. That's for this guy, okay? Then we skip water, we go to this guy. So now C2H3O2 actually goes up. After addition, it goes up by that same number. So all you do is you put these values on the base and acid part, plug it back up in the equation. So pH, the new pH after addition, so this is part A, right? Is pKa of 4.74 plus log of base. So this is my base, so it's 0.110 moles on my base, and then this one is subtract, right? So it's 0.090 moles of my acid. So once we get that ratio, I mean, you could have done molarity, but remember our volume is 1 liter, so the number is the same. And if you divide the moles by the liter, it still get the same ratio. So I just put the moles straight in. Okay, it's some sort of a ratio. So you will actually get the answer as 4.83. And you'll see, yeah, it does go up a little bit. It was at 4.74 in the beginning because it's 1-to-1 ratio. The pH was 4.74, same as the pKa. After you add some sodium hydroxide, it goes up by about 0.1-ish, very small amount. Okay, so that's how you can see the actual calculation of the pH. You just have to basically find the ratio of these, how much it changed. And then for part B, you want to compare it just by putting it straight into water. So we're doing 0.010 moles of NaOH in water, 1 liter of water, right? So your molarity is 0.010 moles over 1 liter. To get the POH, so this is OH here. So POH is minus log 0.10 or 0.010. And you get 2. So the pH would be 14 minus 2, and you get 12. So you see how if you use water, the pH would have jumped all the way from neutral to 12, but if you put it in a buffer, it only raised the buffer just by a little bit. Now, the only time the buffer stops working is when you run out of either of these stuff. Like if you keep pouring hydroxide in, if you pour more than 0.1 moles of hydroxide, you'll run out of your acid and your pH will start jumping like crazy like this guy.
Now that we're done talking about buffers, we want to talk about titrations and tell you how to judge a pH curve. And actually, there's a buffer region in some of the pH curves. Okay, so titrations you've done a lot in Chem 1. So you're probably used to it. There is something in the burette and something in the little flask on the bottom. So you have something on the burette, and then you drop the drops into the flask on the bottom, and you stop the reaction when you reach a color change usually. Color change is the end point where the indicators change color. You have to pick the indicator. Most of the time for lab, we already picked the indicator for you. Indicator will change color at the end point. Now at the end point, moles of hydronium equals the moles of hydroxide. That means it reached equivalence point. So indicator is actually the color, helps you see the color change at the equivalence point. Okay, so endpoint and equivalence point are kind of the same, but equivalent point means hydronium moles equals to hydroxide at that point. And the way we see it at the endpoint is using an indicator. Okay, so let's take a look at some pictures here. So you might be familiar with this experiment where maybe you drop, in this case, they drop hydroxide from the burette, okay, into some sort of acid H plus into the flask. Now, the indicator they use here is phenolphthalein, where it turns light pink at your endpoint. So you drop your hydroxide, you drop. At first it's clear, and then when you get closer, it starts to turn a little bit pink with every drop. And you swirl it every time, but the pink stays longer and longer. And all of a sudden, one drop, one last final drop here will take pink, and then it will, you swirl and the pink stays. If you go past its point, it goes hot pink, and then you probably went too far if you went hot pink. Okay, so these are the experiments you do. Very common indicator is phenolphthalein, okay? Now, one example of titration curve is if you have a strong base and a strong acid. So a good example would be sodium hydroxide and hydrochloric acid. You put, so the way we look at this chart here, this is volume of sodium hydroxide added. That means you're putting in base from the burette into what's in the flask. The flask is an acidic number, so there's an acid in the flask. So from this, I know base is being dropped into acid, okay? Now, the next thing is look at the middle point here. So when you do a titration, there's always a small rise and then a big jump and then a slow rise again. This big jump here right in the middle, smack in the middle of that, is your equivalence point. If your equivalence point is 7, it means there's a strong and strong. Strong acid, strong base, okay? That's the only way equivalence point is 7. If it's not strong, strong, the equivalence point is actually not at 7, okay? So in this case here, I can tell at first I have strong acid, and as I add strong base in, when I add 25 mils, I reach the point where sodium hydroxide OH moles equals to hydronium ion moles from hydrochloric acid. And then once you reach that equivalence point, another little bit of base added will actually jump up a whole lot to the basic region, and then it slows down the addition, slows down the pH rise again over here. Okay, so when you guys do your titration, our goal is always to end somewhere here. Now, we use phenolphthalein in as our indicator a lot. And we always say when you hit the light pink point, that's when you want to stop. That's our end point. So let's take a look if you had the opposite here. When you have strong base being and strong acid. So why is this the opposite? Because this time now you have the base in the flask. So how you look is when I don't have any HCl, the pH is really high. So base is in the flask. And then you add the acid, it drops. And you see there's a drop here, the drastic drop right in the middle. Right in the middle here, that means 25 mils is the volume of HCl needed to get to equivalence point. At that point, moles of H3 or plus and moles of OH minus is the same. Because it's at 7, the equivalence point here, that's how I know I have strong and strong. Okay? Now, there's other scenarios too. What if we had a weak acid in the mixture instead of just strong and strong? So strong and strong was start low, jump, and then go up here. And then the pH equivalence point will be like right here, right? It's kind of like in the middle, and this number will be 7. That, I think that's, yeah, that's the middle of the red line. So at this point here will be 7. Now, if you had a weak acid, it doesn't start at a low pH like the strong acid. The weaker the acid, the higher the pH is. So the weak acid would start at a higher point, and it'll go up. And then the jump is there, but it's less pronounced than a strong acid. Okay, now because it's less pronounced here and it starts higher, the middle of the blue line is somewhere here, compared to the 7 here, the weak acid and the strong base will actually have a pH equivalence point that is higher than 7. Okay, so the way I remember it is if you have strong, strong, the pH ends at 7, equivalence point. If you have weak and strong, the pH is the pH will be higher than 7 if it's a strong base. The pH will be lower than 7 if you have a strong acid. But in this case, we have a weak acid and a strong base. So that's why the pH of endpoint here, equivalence point, is going to be higher than 7. So another example here is we take a look at this titration here. So you see how the weak acid, so earlier HCl starts like 1 or lower. When you have a weak acid, it starts at higher than 2, 3, 4, around this range here. And then it goes up, and then you stop at an equivalence point here. At this point, in the middle of the jump, moles of H equals moles of OH, okay? And then you keep going up here. Then you have the basic region here. So this point here, the middle point, look here, it's 8, it's not 7. Okay, so we always have this assumption that every time you do titration, the equivalence point is always 7. That's actually not true. It's only 7, only neutral, if you have a strong acid and strong base. If you have a weak acid and a strong base, the pH is higher than 7. Okay, so that's one way to tell. Look at where the equivalence point is, right in the middle of the big jump, and look at the pH. If it's higher than 7, you got a strong base and a weak acid. So let's take a region. Look here, they say before the equivalence point here for a weak acid, they call this the buffer region. This is a buffer region because it behaves like a buffer here. If you remember, when you have a weak acid, only just a weak acid, if you add strong base to a weak acid, you actually indirectly generate the conjugate base. Remember the solving the y over 20 minutes y in the lab, and also what we did in lab, how a buffer works in the lecture. So let me show you. When you add a strong base to the acid, you can get the conjugate base being made up. Okay, so again here, alternative way to make a buffer. When you put a strong base to a weak acid, you see that? So this is how there's a buffer region in this chart here. Right here, this part here before it reaches equivalence point is the buffer region. Okay, when you are equivalence point, what happens is because it's pH 8, there's actually a weak basic thing going on. The weak conjugate base is dominating here. You do your calculations for here as a weak conjugate base, like a salt, like an ion calculation. So in this region here, so the reason why we're going through this is because you will have to do calculations for this part, calculations for this part, calculations for this part. Okay, now for a weak and strong here, remember, anytime before the equivalence point is the buffer region, so you use the buffer formulas. And then over here at equivalence point, because it's a higher than 7, it's a basic number, you will be doing pretty much a basic calculation. Okay, it's going to be base of the ion, the conjugate base here. Now, past that point here, after the equivalence point, you have excess hydroxide. This becomes just a plain strong base calculation, how much hydroxide there is, calculation. Okay, so just keep this in mind. We will be doing examples of the calculations, and you'll see it on your review as well. Here's more example. Here's another one. So this one here is if you have a weak base and a strong acid. So how do I know I have a strong acid and weak base? Well, take a look. In the beginning, I have a basic number. And the basic value here is high pH, and it will drop down as you add acid. Now, because the endpoint, equivalence point here is not 7, that's how I know I have a strong acid. Okay, if I have a strong acid, you see how the pH is going to be less than 7 for equivalence point. That's how I can tell you there's a strong acid and a weak base in here. Now, equivalence point is here, that's the volume. So over here, you will calculate this as a buffer region as well. And when you reach the equivalence point, this is an weak acid calculation. And over here is excess hydrogen ion calculation. Okay, so do you need me to write this down for you so you guys can write it? So I'll write it with pencil. So in this region is buffer. Like the first picture that we had, this region here is buffer. Equivalence point is going to be a weak acid calculation. And this part here is excess H+, so it's like a strong acid almost. Well, it's like a strong acid. Once you find out how much excess H+, you just minus log H+ to get the pH. Okay? So one cool thing is, notice here, half equivalence point. At half equivalence point, the acid, the base, and the conjugate acid is the same. So base and acid ratios is 1 to 1. pH equals to pKa. Okay? All right, so you gotta remember that. Now, if we go to this picture before, let me go back to the picture before. Right here. 25 is my equivalence point, so about 12 and a half. So like right here, over here, you have pH at this point equals to the pKa. So the pH is like almost 4, so your pKa is almost 4, whatever that value comes up. Okay, so at half of the equivalence point, you will be able to find the pKa. All right, so let me draw this out. So if we were to draw it out here, and then we'll write it like notes of where things are. So here's an example. After we learn to identify all these graphs, we will be doing calculations, okay? So let's do a strong picture first. Strong will start on a lower. So I guess we'll do an acid first. Acid in a flask, and then add strong base, and then you see the big jump, and then slow again. So right in the middle, this is kind of the middle, right? Yeah, it's middle. So we call this 7. So this is pH. This is volume. What are we adding if the pH is going up? Volume of base added. Okay, now because it's 7 right here, the base probably is a strong base, and this is a strong acid. Okay, so I'll write down, I can tell this is a strong base. And the red line here is the whole red line is strong acid. Okay, now for strong acid, you don't have to talk about pKa or whatever. It's just this right here. Just know that this is a pH 7 equivalence point. Now, if you had a weak acid, let's see, different color. The weak acid would start at a higher pH, and then it will also have a big jump, whatever it is up here. But the jump here, like somewhere in the middle here. So this pH here is going to be higher than 7. So this is maybe like 8, 9-ish. Okay, so, and then you see how this guy here is exactly at 7. So the blue line here is going to be for a weak acid line. So the weak acid and the strong base gives you a higher equivalence point pH. Now, for the weak acid, if you go halfway of the equivalence point, like say this is a halfway volume, right? This point here, what can you find? At this point, pH equals to pKa. All right. Now, if they were to ask you a question here, now these have come up on a test before, where they put 4 spots. So they also made a make-believe spot here. They call this D, they call this A, they call this B, and they call this C. Okay? So we just learned that the blue line here is titration of weak acid and strong base. Right? The red line here is titration of strong acid and strong base. They'll ask you which point is the equivalence point. They'll give you this graph here. They'll say A, B, C, or D. Which one of these is the equivalence point of a weak acid to a strong base titration? then you'll have to say, well, based on this picture here, B is the equivalence point position of the weak acid and the strong base. And then they ask you, what is the equivalence point of a strong acid and a strong base? That would be A. A is the equivalence point of strong acid and strong base. And then they say, what is the equivalence point? And what is the pH? What is the pKa of the weak acid? Where can you find the pKa of the weak acid? Then you will put C. D is just a distraction there. Okay, so just remember C here is where you find the pKa, because pH equals to pKa at half equivalence point volume. So if it was like, this is the full volume, half the volume, that spot there is where you find your pKa. And you only have that for the weak and weak acid or weak base. So well, let's draw a picture of the other one, the opposite of this, okay? So remember, this right here is the buffer region. This here, this equivalence point calculation is a weak base ion calculation, okay? And over this range here, the blue line here will be excess hydroxide. Actually, I mean, for the red line is also excess hydroxide. Now, the strong acid, strong base does not have a buffer region, okay? And this pH you don't really need to calculate, because as long as moles of H equals to OH is pH 7. So the trickier one is actually the weak and strong chart, okay? We'll be doing strong, strong, and weak, strong. So let's go to the next graph here. You can draw the same thing, but now just the opposite scenario. You have strong base, drop, and then strong acid. And then the middle here will be 7. Okay, so the line here, titration, strong base and strong acid. So basically volume of strong acid added. Now, if we had a weak base in here, it would be start somewhere a little lower, and then it would have a, well, my curve is kind of ugly now, but it's not as pronounced, okay? Sorry. But maybe like somewhere like right here is the middle. You can do better than me at drawing, but this pH here is less than 7, okay? Now, if you wanted to find a pKa, is basically whatever the volume is here, half of that. You'll find whatever that pH is, that's the pKa spot. Okay, so if it's like around here, it looks like 7, 8, 9, maybe it's around 9, the pKa will be around 9. Okay, so this is where you find the pKa. The pKa is equal to the pH of the graph, whatever that point is. So the blue line is titration of weak base and strong acid. Now, again, this region here is buffer region. This spot here is a weak acid calculation. This spot here will be excess H plus calculation, like a strong acid, strong base. Okay, so let's go ahead, since we know how to figure out where to find. So a lot of times they give you pictures and ask you how to determine these positions, or what are you mixing together? How can you tell it's weak and strong? How can you tell it's strong? And then sometimes we have to do calculations. Okay, so let's go ahead and do calculations. We'll start with a strong acid and a strong base one first. Now we'll go to a weak strong example. Okay, so the first example calculation is going to be 50 mils of 0.200 molarity NaOH is titrated with 0.200 molarity HNO3. Calculate pH of A after adding 30.0 mils of HNO3, B at equivalence point. Okay. So right here, let's use some blue pen. Use blue pen. At equivalence point, the molarity of the base is sodium hydroxide is 0.2. Molarity of acid is 0.2 also. You have to be careful. Let's write the equation out to make sure you don't have a polyprotic or sometimes your hydroxide has double OH as well. So the equation here is actually NaOH plus HNO3. You'll make H2O and NaNO3. So the ratio is 1 to 1 to 1 to 1. Okay? So ideally, so the mole ratio is 1 to 1 here. That means if you have 50 mils of 0.2 NaOH, for you to get at equivalence point, moles OH equals to moles H, right? So you would need how many mils of 0.2 of the acid? You would need the same amount. So you don't really have to calculate this. We know we use 50 mils of 0.2 molarity HNO3 will give you the equivalence point. Now, because this is strong acid and this is a strong base, the pH of equivalence point is going to be 7. You don't really have to calculate that, right? Because it's going to be at 7. Now, assuming this is all going to be at room temperature, okay? Now, if you add 30 mils, you're not quite at 50. What's the pH going to be at? You can tell it's going to be, it's not going to be 7. And what does this picture look like? So a base is titrated with acid. So you have base in there. You start off with base. So the picture is where you have a high pH and then it drops and then it goes down. So the equivalence point here is 7. So this was like 50 mils here. They're saying find out where 30 is. So that's the point you're having to calculate. It's going to be a pretty high pH here. Okay, so just keep that in mind. You're not adding enough acid to reach equivalence point. The pH will be kind of high. But how can we calculate this? At this point here, H and OH are equal at equivalence point. At this point here, you have actually excess of hydroxide. So this region here, you have excess hydroxide. Okay, so because it's excess hydroxide, all you have to do is calculate how many moles of hydroxide there is. And then we find the molarity, we get the POH, and then we get the pH. So let's go ahead and do that. If you have 50 mils of 0.2 moles of sodium hydroxide and you added 30 mils of HNO3, so really you have an excess of 20 mils of 0.2 molarity NaOH left over, right? We still have that hanging around before I reach the equivalence point. So find the moles of this. So 20 mils of 0.2 molarity. So go ahead and find the moles first. 1 liter is 1,000 mils. 0.2 moles of NaOH or OH is the same thing, right? So I can write NaOH. And really it's just the moles of OH because Na is the spectator ion. 1 liter, that's from the molarity. I will get the moles here. So this moles is 0.0040 moles for 00. Now, that's not helpful yet, but now I know the moles of hydroxide. What is the molarity of my hydroxide? So to get the molarity, you have to remember molarity of hydroxide is moles of OH divided by total volume in liter. What's my total volume here? You have 50 and then you added 30. Your total volume is 80 mils. Okay, so that goes on the bottom here. So 80 mils, you change it to liters by dividing by 1,000, so 0.0800 liters right here. That's the total volume. My moles of hydroxide is just the same as moles of sodium hydroxide. So let's put this in there. And then we can get the molarity. So the molarity comes out to be 0.050 molarity. So therefore my POH is minus log of OH, which is this guy. Which gives me 1.3. Therefore pH is 14 minus 1.3. You get 12.7. Okay, now if they had a question, they added another one and say, what is the volume, what's the pH of somewhere over here after you add 60 or something. Let's go ahead and add it. We'll add the question right here. Let's see. Okay, so this is before equivalence, after at equivalence, and then we'll do one that's after. So maybe we'll do after adding so 50 is exact. So maybe we add 60 mils of HNO3. Okay, if you add 60 mils, that means you have 10 mils excess of 0.2 molarity HNO3. Okay, in that case, all you do is find the moles and then find the molarity and then you need the pH. Okay, so 10 mils, I'll do the same math over here. One liter, 1,000 mils, 0.2 molarity or moles of HNO3 is to 1 liter. So your moles is 0.002. Sorry, running out of space already got a small. 0.002 moles of HNO3, which is also the moles of H plus. Okay, so the molarity is going to be the moles of H plus, the same as nitric acid, divided by the total volume. Now, what's my total volume now? I had 50 and I have 60. So now it's 110. So it's 0.110 liters because the total volume goes there. So let's see what the molarity comes out to be. 0.018. Well, we keep 3 6 because 182. And then to get your pH, okay, I'm gonna write like over here. The pH is minus log of this guy. .74. Okay, so make sure you're able to do this. Now, if I flip the question around and put like the acid in first and then the base, basically same idea. Okay, I'm not gonna do the math, but you should be able to tell that if we had a strong and strong, let me just draw it on the other page. Are you guys done writing this? Everyone good? Okay, so I'm gonna go ahead and change the page, and now I'll draw the chart out here. Now I showed you the example of if there's a base and then you add acid, right? If we did the opposite, the math is still gonna be the same. You just have to find out what's left over and what the total volume is, okay? So I'm not gonna do the math because it's gonna get so long, but you should be able to do it. Let me write it so you have it in your notes on how to do it if you see that question. So if we had a question where they said, now let's go ahead and start with it was base and then you add acid, right? So now let's we do like something like this. Now remember this is equivalence point. So whatever the volume is, let's say it's 50 again, 0.2 and 50. So this is page 7. Volume, strong, base, added. Okay. At equivalence point, the pH is 7. You just have to make sure you calculate the moles of OH here. Moles H equals 2 moles OH. Okay, that's the point that you have to calculate for that 7. If they ask you for the volume, you just make sure the volume comes up to where the moles are equal. Now, in this region here, you don't have enough yet, so you have to calculate the moles. So at this point here, H and OH are equal. At this point here, you have X. You still have too much H, so you get the moles of H that's left over, and then you divide it by the total volume, right? And then you get minus log of molarity of H to get the pH. Now, for the top part here, you have excess hydroxide. So you just find moles of the hydroxide that's left over, and then you divide it by the total volume, whatever volume you have in that case, and then you get POH from that because it's minus log of OH, and then you get pH. It's the same idea as what we just did, but if they flip the picture around, this is what it would look like. Okay? All right. Now let's do a weak strong calculation. So as you notice, the weak strong calculation will have like buffer regions, we'll have weak acid, weak base calculations. So it depends on the example. So remember, I showed you the kinds of regions. We have the buffer region before equivalence point. At equivalence point, if it's higher than 7, it's a basic problem. If it's lower than 7, it's an acid problem. And then at the end here, if it's a lower pH, it's excess H, kind of like a strong base, strong acid calculation earlier. And this is excess hydroxide, okay? So the only difference is these 2 points here are kind of special. One's a buffer region, one's a weak base or weak acid region. So let's go ahead and set that question up. We are going to do 40 mils of 0.100 molarity of HNO2. The pKa is 3.34. Is titrated with 0.200 molarity of KOH. Calculate a volume required to reach equivalence point, and then B, pH after adding 5 mils KOH. C, pH at half equivalence point. Remember that what this is pH half equivalence point, that's actually a pKa. So the answer is already there. But I want to show you, like, if you did a chart, I'll prove it to you why pH and pKa is the same at that point. But You don't really have to do the math if you already know at half equivalence point pH is pKa. But I'm going to do it to show you, okay? D pH at equivalence point, E pH after adding 21 mils of KOH. All right. So hopefully you guys are done writing. I'll give you a little bit of time. We'll go ahead and want to process the step by step here. We'll start with A. A says how much volume of basically KOH, I guess I should write down KOH, required to reach equivalence point. So at equivalence point, you have to remember H and OH are equal. So we'll find out how many moles of H, and then we'll need to know how many moles of OH to match it. So in this case here, in step A, equivalence point means moles of H equals to moles of OH. So I have 40 mils of 0.1. So 40 mils of 0.1 molarity HNO2. So we're going to do the math here to find out how many moles. So in case you don't remember, I'll write it out. 40 mils, and then 1 liter is 1,000 mils. And then you take your molarity, 0.1 moles, 1 liter. So that's how many moles you will get, right? So in this case here, this one you get 0.004. So you're going to need 0.004 moles of OH. Okay, so you need 0.004 moles OH. So what was the molarity of KOH? 0.2 molarity of KOH. So, I mean, if you couldn't do this in your head, you could calculate and find how many mils, but because this is double, exactly double, right? You will know that you're going to need 20 mils. Agreed? So if you couldn't do that, then you just take the moles and use the molarity, and you can calculate the volume as well. I'll just write down the equation just in case you want to have an example. So you will start off with 0.004 moles. And then you know that 1 liter has 0.2 moles of KOH. And then you convert to mils, where 1 liter is 1,000 mils. This would give you, in this case, 20 mils. Okay, now, so that's the answer, 20 mils for part A. Part B, it says, what's the pH after adding 5 mils of KOH? So what's the pH at half equivalence point? So we can go ahead and do part B. After adding 5 mils of KOH. So in this case, it's actually going to be a buffer region, because they gave you the pKa of the acid. That means it's a weak acid and a strong base. You have to know group 1 hydroxide is strong base. So the picture looks like this. It's a weak acid at base, and then you jump up. The equivalence point here, this is higher than 7, so higher than 7. And And this is the volume of KOH added. So we just learned that the equivalence point volume was 20 mils. Right? We just calculated that part. So now they're saying at 5 mils, so 20, 10 is right here, so 5. What's the pH over here? They're asking that for part B. Okay? So we're gonna do, remember this whole region here is a buffer region. We're gonna do a buffer calculation. So I'm gonna go ahead and write out the equation. You have, when you add a strong base to a weak acid, okay, what happens is the weak acid self-sacrifices to neutralize whatever strong base you get, and it will create the conjugate base and water. Okay, so I'm going to go ahead and do the chart again, like the before addition of OH, and then the addition of OH, and then after addition. Okay, so before addition of OH, we need to find out how many moles of HN, before we put in any OH here, we need to find out how many moles of HNO2 was there. Well, we kind of calculated that earlier, right? We calculated the moles to be 0.004. So I'll go ahead and put this down. And then before you add any hydroxide, there's none of these guys either. So we'll put 0 and 0. And water is liquid, so we don't want to worry about it. Now what we're going to add 5 mils of 0.2 molarity KOH. So you have to find out the moles of 5 mils. So if you can't do this in your head, like 20 mils gives you 0.4, 5 is 1/4 of that, so it should give you 0.001. Can you guys see that? Okay. If you can't follow, I will write the math out. I just didn't want to write a whole ton. I'll write down that this came from 5 mils of 0.2 molar KOH. Okay? You have to calculate that part, but I kind of can see it in my head that if I have 20 mils, it's 0.004. So 5 mils will be 0.001. So I'm going to put that here. And then if you add 0.001, 0.01 of this guy is going to react with that to neutralize it, so this guy goes back to 0. So that means now my HNO2, now I have 0.004 minus 0.001, so I actually have 0.003 left over. You guys agree? And then now, because I sacrificed 1.01 here, this one is going to go up by 0.001. Do we follow this? Okay. Now that I have the base and the acid, I can go ahead and do my buffer equation. Okay. So the calculation would be pH equals to pKa plus log of base over acid. So in this case, this is my base and that's my acid. So I write 0.001 over 0.003. And we're going to take a log of that and add it with the pKa, which is given in the question, 3.34. So in this case, you should get pH of 2.86. Let's try it out. Make sure you guys can do that. Yep. Everyone good? Okay. So that's part B. Part B says if you only add 5 mils, this is how much hydroxide, and then you have to do the buffer kind of calculation, and you end up with your 2.86 pH. which makes sense because it's really low somewhere down here. Now let's do part C. Now, because I already told you part C at half equivalence point, pH is equal to pKa, you actually don't even have to calculate. You just need to know by default that's the answer, 3.34. I want to show you how I got 3.34 so you understand that people are just not making it up. There's a reason to it. The reason actually is really similar to this. So I'm going to redo this chart here. And let's do a different color this time. You have OH, HNO2, you have NO2, and H2O, right? So same buffer region still. But now the before, the addition, and the after. So the before number stays the same. You have 0.004 moles of this guy. Everybody else is 0. And your addition, now 5 mils was 0.001. What's 10 mils? 10 mils will be half of this, right? So 0.002. So in this case here, the HNO2 will reduce by 0.002 to get 0.002. So this is 0.004 minus 0.002 versus this one is 0 plus 0.002. So you get this. So you see how now the base and acid is the same number? So pH equals to pKa plus log of base over acid, which in this case is 1 to 1, 0.002 and 0.002. That's why pH equals to pKa. Okay, so just remember this. You don't have to do this part. If you remember at half equivalence point, the base and the acid ratio is exactly the same, which pH will be equal to the pKa at that point. Now, let's continue. So we did ABC. Let's do pH at equivalence point now. So we did this buffer region calculation. We also know that this is now they want you to calculate the pH equivalence point. So we did all the stuff before this. We know what the volume is to get there. We know you need 20 mils. But now they want you to calculate exactly what the pH is. We know it's going to be higher than 7. Okay? So if you know it's higher than 7, it's going to be a basic condition. So at that point, at part D, what base is there? So if you notice, once you put in 0.004, so like in this picture here, so the more hydroxide you put in, at that point, if you put 0.004 here, this would turn to 0, agree? And then you'll end up with 0.004 of the conjugate base. Okay, so that's the idea there. So let me write that on part D. For part D, the reason why we have to do a weak base calculation is because you keep adding that hydroxide to the acid, the weak acid, you end up making conjugate base and water. You put just enough, so before addition, you don't have to write it out when you. I'm just writing a lot of steps out for you now, so you can learn it better. So before was 0.004, and this was 0 and 0, and then you add 0.004, right? So then this becomes 0. This is 0, and now you have 0.004 of this conjugate base. So that's what's giving the pH of a basic value. But a weak base, can you guys see the screen? Okay. Yeah, I can see it just fine too. Or maybe try logging in and out. Maybe it helps. Okay, so we have 0.004 here. So now it becomes a weak base problem because this is my conjugate base. Okay. So if I have NO2 negative as a base, I want to write an equation, add it with water. And then we'll go to, if this is base, add a proton, so HNO2 plus OH minus. So this is a weak base problem. So you need to find Kb of NO2. Do we have Kb of NO2? No, they didn't give it to us. You know what they gave you? They gave you pKa of HNO2. What was it? It was 3.34. So here's the shortcut. If you know the pKa of HNO2, pKa plus pKb of the counterpart equals to 14. So I'll write it out. pKa plus pKb equals to 14. So pKb is 10.66. Okay, if I know the pKb is 10.66, I can take minus log of Kb equals to 10.66. Remember that formula? So now I can find Kb by putting log of Kb equals to minus 10.66. Kb is 10 to the power of both sides, equals to 10 to the power negative 10.66. So I get my Kb as 2.188 times 10 to the minus 11. Everyone good with this calculation here? Another longer way is if you found the pKa and get it to Ka first, and then you take Ka times Kb equals to Kw. You can get the same answer here. Okay, so once you get the Kb, we gotta put that in here. That equals to 2.188 times 10 to the minus 11, and that equals to what formula? HNO2 times hydroxide over NO2. Now you see like all the chapters are linked together. Even though we're in chapter 18, we're now doing problems from chapter 17. Like it's all linked together. Okay, so once we do this part, what do we do next? We set up the ice table, okay? So in the ice table, we don't have to put water, but we do need everybody else. So initially, how much, what's the molarity of my NO2? So here's another part where you need the molarity. We have to calculate the molarity. Do we know the moles here? We do, right? We have the moles here, but we want to put molarity in here. So molarity of of NO2 is gonna be, I'm gonna do the side calculation over here. Zero 0.004 moles divided by, what's the total volume? We said at equivalence point it was 20 mils of, we added 20 mils to 40 mils, right? Gotta remember that. So let me go back here and see. So we said it was 40 mils and 20 mils to reach equivalent. So the total volume here is going to be 60 mils. So 60 mils is 0.0600 liter. So let's get a molarity here. 0.0667. I had the zeros here. I was dropping them earlier. Okay, so that goes in here. So then you have none of these guys in the beginning because all of it turned to 0, and you also don't have any hydroxide. But because it's a weak base here, the change is minus x plus x plus x. So you have x and x and 0.0667 minus x. So do we want to do the shortcut? Yes, because this is so small. And this number is bigger than that, more than 10,000 times, right? So I'm going to go ahead and do the shortcut where we set the KB up. Now it is 2.188 times 10 to the minus 11 equals to this and this, so it's x times x, divided by 0.0667 minus x, but we cross this guy out from our approximation. Okay, so x squared equals to 0.0667 times 2.188 times 10 to the minus 11. These two values multiplied together, you should get 1.459 times 10 to the minus 12. Let's double check it. Times 2.188 minus, yep, 1.459 minus 12. And then we take the square root of that, we can get what x is. 1.21, yep. Well, 1.21 or 207, 208, 10 to the minus 6. And then you can always check your step, but I can tell it's really, really small. You don't really have to if you don't want to, but let's go ahead and do it anyway. Let's do a check step. 1.208 times 10 to the minus 6 divided by 0.0667 times 100. One 1.81 times 10 to the minus 3%. So it's okay to approximate. So we know our x here. Our x here is 1.208 times 10 to the minus 6 molarities. That equals to molarity of hydroxide. So I can get the pOH minus log of that value, which will give me 5.92. pH will be 14 minus 5.92 equals to 8.08. Okay, so this is a weak base problem. All right, now the last part, we want to do pH if you add 21 mils. So 21 mils is past the equivalence point. So all you just have to know is find out how much excess hydroxide is there and divide by the total volume to get the molarity. So let's go ahead and do this. We added 21 mils, right? So 21 mils to 40 mils of 0.1 HNO2. So you have an excess of 1 mil of 0.200 molarity KOH. Agree? So our excess here is that. So let's find the moles of this and then divide it by the total volume, which is 61 mils in liters. Okay, we got to turn into liters. Let's go ahead and do that. So 1 mil, we actually did the calculation earlier. So 1 mil, 1,000 mils is 1 liter. And then we want to do the molarity, 0.200 moles over 1 liter. So you have 2.00 times 10 to the minus 4 moles of hydroxide. So that's the moles. What's the total volume? The molarity is moles of OH over total volume in liters. The total volume was 61, right? So we put the moles. And then we divide it by 0.061 liters. And you get 3. And really, it's 6100. I'm going to add my zeros there. So it's 3.28 times 10 to the minus 3 molarity of hydroxide. So POH equals the minus log of 3.28 times 10 to the minus 3. That equals to 2.48. pH is 14 minus 2.48, so you get 11.52. Okay, so this is the version where you have a weak acid and a strong base, right? So we did the calculations according to the types of regions they had. I didn't do the other way, but just remember we talked about it. Before equivalence point, you always do the buffer region. At equivalence point, you do either weak base if you have a pH that's higher than 7, or weak acid if it's pH that's lower than 7. And then after equivalence point, depending on what's excess, if it's excess hydroxide, you do this. If it's excess hydrogen ion, you just find out how much hydrogen ion divided by total volume, you'll get the pH. Okay? So this is that part here for the titrations and acids and bases and buffers. Now we want to move on to the something called solubility product. So in this case here, before we do that, I'm going to see this. This is kind of cool. Just to see how this is strong acid on the bottom. The weaker the acid is, the smaller the jump will be because the higher the pH it starts off at. So this is kind of cool to take a look at. So that's slide number 37. All right. And then might as well. pH, pKa is that point at you have half equivalence point. We just proved it to you in math. Now, if you had a polyprotic acid, there actually would be 2 equivalence point. But in lab, it's really hard to catch it. You have to be really, really slow to catch, like adding 1 drop at a time to be able to catch this. We're not going to have to worry about calculations for this, so don't worry about that. I just wanted to show you. So remember phenolphthalein indicator? It's good for, you see how light pink is pH around 9? So that means it's only good for a case where it's a weak acid and a strong base titration. If you use strong and strong, the pink actually is too far gone because strong and strong ends at 7. Weak acid and strong base will add 8 will turn pink around 8 or 9-ish. So phenolphthalein would work good for that. So just keep in mind that, like, you know, when you do titration, when you see the light pink, if you were using phenolphthalein, it was actually good for a case where you had weak acid and strong base, and the pH wasn't 7. The pH was actually a little higher than 7. So you can see here, different indicators have different regions of changing colors. Like you couldn't use methyl red in this case because it's too low. You wouldn't be able to catch the equivalence point. But phenolphthalein is right there where it can catch the change, the light pink. That's where it turns color for, and then it matches the equivalence point. Now, so the next part here we want to talk about is KSP, which is what you'll see in the lab stuff. Solubility of product. So basically they're saying anytime you have insoluble solids, in Chem 1 you probably memorize like the precipitation. Some of them will precipitate, some of them won't. Well, those guys that precipitate, they say it's not soluble in water. When they say they're not soluble in water, they're actually not telling you the complete truth, because very, very, very small fractions of these actually are soluble and turn into ions, even though they're an insoluble solid or doesn't dissolve in water. Okay, just a very small amount. So you can actually write a reversible reaction for any insoluble solid and say break into small amounts of ions. So if you had to write the K for this, because this side is solid, you would literally just have the ions. So it's Pb2 plus and Cl negative. Because there's a 2 coefficient, you have to square it. Same like what we've been doing as usual, but the only thing is now is K of solubility of product. So it's KSP. So we had Ka, Kb, Kw, now we have KSP. We also had Kc and Kp before that, with concentration molarities and P for ATM. This is KSP here. Okay, so just keep this in mind. This is how we write the formulas. And this is the reason why you have to square the Cl molarity when you calculate KSP in the lab, because there's 2 Cl. If you were doing for AgCl, there's 1 to 1 to 1. You wouldn't have to square the Cl for AgCl. It just, the reason that we have to square the Cl here is because there's 2 chloride ions available every time you break it apart. So because these are really, really small numbers here of ions, the KSP is going to be a small value because the molarities are going to be super, super tiny. Okay, so super, super tiny. Let's see. So you see how they're all so super small. But there's a list of them. And sometimes you get to calculate stuff with it. But, you know, just an idea showing you that all of them are pretty small. Okay? Now, when they're small like this, means they barely dissolve. So solubility is the amount of solute that will dissolve. So how soluble is it? So we calculate something called molar solubility, and we use the unit molarity still, because it's moles of solute that will dissolve in 1 liter. So molar solubility will still be use unit molarity. Okay. So the unit for molar solubility is molarity, and we're going to symbolize it with S because we're talking about solubility now. So let me zoom out, and we will write some question here. So KSP of PbCl2 is 1.17 times 10 to the minus 5. And it says calculate S the molar solubility of PbCl2 in pure water. Okay, so to do this, you have to find S, which is the molarity. So what you have to do is write the equation. PbCl2S breaks down to Pb2 plus AQ plus 2Cl negative AQ. Okay, so the KSP formula is Pb2 plus and Cl negative square. So to do this calculation here is really the same thing like what we've been doing. Actually, it's really simple compared to what the math is a lot easier. ICE. Initially, there's no ions at all. So you have plus S. So we don't do X now. We call it S because S is a solubility. And this is 2S because there's 2 here, sorry. So this is S and 2S, and then you plug it up here. So KSP is 1.17 times 10 to the minus 5 equals to S times 2S squared. So this becomes 4S cubed equals to 1.17 10 to the minus 5. So S cubed is 1.17 times 10 to the minus 5 divided by 4. And then you take a cube root of all of that, you get 1.43 times 10 to the minus 2 molarity. So this is the molar solubility. Okay, now what does molar solubility mean? It means like how soluble the thing is. So one important thing is you don't want to compare KSP. So sometimes they'll ask you, which one of these is most soluble? Which one of these is not as soluble, least soluble? Solubility depends on the S. The most soluble means the highest S. The least soluble means the smallest S. Do not compare the KSP unless the number of ions is the same. So in this case here, if you have 3 ions and versus 2 ions, you can't compare using the KSP. You have to calculate the solubility. But if you have both of them as 3 ions, the formula for solubility is the same. You can actually look at KSP and determine the solubility. We were talking about KSP last time and molar solubility. I'm talking about how you can determine who's more soluble, who's less soluble by looking at the molar solubility, okay? The S tells you how soluble it is. The bigger the S, the more soluble. And if they have the same number of ions, you actually don't have to calculate the S. You can look at the KSP and determine solubility. But if they have different ions, like this one has 2 ions, that one has 3 ions, you don't want to use the KSP to compare because the solubility will come out a different trend, okay? Not always, but a lot of the times. So continuing from the previous question, here's another problem. It says the molar solubility of Ag2SO4 in pure water. So notice the questions are all saying in pure water right now, and later on we'll do something that's not in pure water. Is S equals to 1.2 times 10 to the minus 5 molarity. Calculate KSP. Okay, so the previous question wanted us to get the S from the KSP that's given. Now we want to do, here's the S, find the KSP. Okay, same idea. If you have this guy, you have to write the equation for this solid. So the solid is Ag2SO4, and this is the solid, and then it dissolves. Okay, it dissolves to Ag positive, there's 2 of them, and sulfate. Okay, so when you have that, you break into Ag plus, and then SO4, 2 minus, and then ICE. So when it's water, initial is 0. When it's not pure water, you'll have some ions there, so these won't be zeros, okay? And then because silver is 2 here, it's going to be plus 2S. Sulfate is just 1, so it's plus S. So it's plus 2S plus S. And then that means KSP for this guy is Ag silver squared, and then SO4 2 minus, which means this guy is 2 plus 2S squared, SO4 is squared. I mean, not just S. So that will give me 4S cubed. Okay, so once you see this is 4S cubed, notice this one up here also had 3 ions, and it's also 4S cubed. See that? So that's why the number of ions is important. If it's the same number of ions, the pattern for the KSP is the same as the pattern for S. But if it's different ions, the formula comes out different. So in this case, KSP here, each S is 1.2 10 to the minus 5. So all we do is plug it in. To the power of 3. And you get your KSP to be 6.9 times 10 to the minus 15. The KSPs are always going to be small numbers here. So now let's try some calculating stuff that's not in pure water anymore. So remember, if it's pure water, your initials are 0, 0. Now let's try something that's not in pure water, okay? So I'm gonna go ahead and change the page if you guys are ready. Says, what is the molar solubility of CaF2 in a solution of 0.1 molarity NaF. So now it's not in water anymore, it's in NaF. KSP of CaF2 equals to 1.46 times 10 to the minus 10. So if they're asking now for S of CaF2, they gave you the KSP, and now it's not in pure water, it's in NaF. So if you have a solution of NaF, you'll have some ions of Na and basically 0.1 molarity of Na plus, 0.1 molarity of F negative. Na here is the spectator ion because CaF2 is a solid and it breaks into calcium ion and 2 fluoride ions. So KSP is Ca and then F negative square. Okay? Now, because this is not in water, it's not 0 in the initial for your ice table. You have 0.1 molar of Na, 0.1 molar of F. So that means instead of 0, 0, you have 0 and whatever the value, which is 0.1 for initial for F. So I'm going to go ahead and write it out. Ca2 plus and then F. So ICE. So initial for water, it was 0, 0, right? Now it's not 0, 0, it's 0 and 0.1. Okay. So this here is plus S plus 2S. So it's S and 0.1 plus 2S. You look at the solution here to determine what ions are available in the solution. If it's pure water, there's no ions. But if it's a solution of NaF here, you have Na and you have F, but Na is not even in the equation. It's not in the ice table, so you just ignore it. It's a spectator ion. But F here exists in the equation and on your ice table. So that's why you put the 0.1 molarity here. So you have to just see what the question gives you, okay? So let's set it up. The KSP is given. This one is 1.46, 10 to the minus 10. That equals to S, and then 0.1 plus 2S squared equals to this number. Now, your K is really, really small, right? Is it really, really small compared to 0.1? Yeah, it's like 10,000 times smaller or more. So we can go ahead and assume this 2S here is going to be so small that it's insignificant, okay? So basically we're using our approximation here. Now, if that happens, now S will equal to basically this part. I'm going to put it down on the bottom here. So 1.46 times 10 to the minus 10 divided by 0.1. The 2s is gone, so just take 0.1 and square that. So you get your answer. S is now 1.46 times 10 to the minus 8. Okay, now as a comparison, in pure water, if you calculated this question like what we did in the previous question, where you do the 0, 0, you will calculate the S for CF2 to be 3.32 times 10 to the minus 4. You see how in water it's a lot bigger? And then if you put it in a solution that has the common ion F here, it becomes a lot smaller. The reason why this happens is the common ion effect. If it's just plain this guy here with no other extra stuff, it reaches equilibrium. And then you added some extra F. What happens is it pushes the equilibrium to the equation reaction shifts to the left. So less of it becomes soluble, and that's why the number gets smaller compared to in water. When you have a common ion, it becomes less soluble. The more common ion you have, the least soluble it will be, okay? In comparison to pure water. So now the next thing is we want to see if things will precipitate or not. So a lot of times we say this is not soluble. And then, but a little bit of it turns in ion, there's an equilibrium here. So the KSP is given. So if you were to actually calculate the Q, you can compare Q to K and see if it's going to dissolve or not. So I wanted to show you this here. If Q equals to KSP, the solution is saturated. It's just right, just at saturation. You don't have to precipitate anything yet. But as long as Q goes over the saturation level, Q bigger than that, then you will start precipitating, okay? So this idea here is where you had the lab last week, where you added, you had some source of PV ions and you some source of Cl ion, and you had to keep adding the Cl until at one point it precipitates, because at one point you add enough Cl in the concentration, your Q becomes bigger than K, and then it precipitates. Okay, hold on a second. Let's see. Is it still blurry now, guys?
It's a little better.
My computer does this auto run for the scan and I can't stop it. Hold on, it says I can't minimize it.
It looks good now.
Is it better now?
Yeah.
Okay, because like it just pops out and does it on its own and I can't stop it. So it's probably just because my computer is thinking harder, so it gets blurry. Sorry about that. All right. So back to over here, I was talking about Q versus K. So in our lab, you have to keep adding Cl until the Q. So basically Q is just the concentrations of whatever ions you have. And then as soon as I have enough concentration, the Q is bigger than the K, then you precipitate stuff. If the Q is equals to K, is saturated solution, you don't have to precipitate anything. And if Q is less than K, is unsaturated and you don't have precipitation as well. Okay, so just keep this in mind. When Q is bigger than K, it's above saturation, and Q bigger than K can also be supersaturated solution. That's how you make your crystals actually. So like something that's supersaturated, you just touch it, and then it will become a big seed crystal, and then it will just grow. The other crystal will grow on it. Will get bigger. So basically, you have to keep adding the drops until you suddenly see the precipitation, okay? You have to add till the molarity is high enough, basically. So speaking of dissolving and stuff, I'm going to talk about how pH can actually affect solubility too. After this, we'll do some calculation on Q versus KSP. So if you have pH here on solubility, so let's say we have an higher pH means more basic, right? More basic means more hydroxide. If it's more acidic, means it's more H+, okay? So it says here, if you have this metal hydroxide, so just insoluble hydroxide, so this metal plus a hydroxide, this is a solid, and then breaks into ions here. Now, if you have a lower pH, okay, a lower pH means more acidic, right? More acidic means there's a lot of H plus floating around. If there's a lot of H plus floating around, H plus is going to react with the hydroxide, and every time you steal some hydroxide to react with H to make water, you're actually stealing away some of the product. So the reaction will shift it to the right. So the lower the pH, the more soluble this thing will be. On the other hand, if you increase the pH, there's a lot more hydroxide. The presence of hydroxide over here is excess, so there's extra of this is going to shift it to the left and make it less soluble. So pH does play a matter if you have insoluble hydroxides here. Now, another example here is, let's say you have another compound and the anion is weakly acidic. It says here, an anion or weak acid, so it's weakly basic, okay? So in this case, your carbonate is the basic source, okay? So this is the ion the insoluble solid. It will break into the metal ion and the carbonate ion. Now this guy is slightly basic, where it can take on the proton over here. Okay, so there's a second, because this guy is basic, it can do another reaction. Carbonate can take the proton and make bicarbonate here. So every time it's in water, right? So you'll have hydronium ion. Every time you have lower pH, you have more hydronium ion concentration. So the presence of the hydronium, if you have a low pH, is really, really high. It's gonna steal the carbonate here to make bicarbonate. So every time you make carbonate, it gets used up in the next reaction. So it just makes it more soluble. So in this case, the more H plus available, which means the lower pH, the more acidic, the higher the solubility will be. So it's not necessarily asking you to memorize these things, but sometimes you will see scenarios that shift it to the right, which makes it more soluble, shifts it to the left, which makes it less soluble. Okay, so you just gotta keep in mind that pH can now also play a part. So we were talking about common ions here. So like in this case earlier, we have CF2, and then this was the common ion. Because the presence of F is here, it pushes it backwards. So your solubility becomes a lot smaller. Okay, so let's go to the next part now. Where we want to go ahead and calculate the Q compared to K and see if something precipitates out. Okay, so here's the question. So PbNO3 2. So this is an aqueous solution because it's nitrate, and it's mixed with NaBr, another aqueous solution, to form a solution of 0.0150 molarity PbNO3. So they're giving you the molarities after you mix them. And 0.00350 molarity NaBr. And they say, thus a precipitate form. KSP PbBr2 is 4.67 times 10 to the minus 6. So when they give you the KSP for that guy, that is your solid. So if I know that's my solid, I want to go ahead and write an equation for it. Pb, not Cl anymore, it's Br2. It's going to break into ions. Okay, and the formula KSP is Pb2 plus times Br negative squared. And that equals to 4.67 times 10 to the minus 6. All right, so now that we have this, so this is the K. this molarity here is the Q. Because they're asking you, based on what the molarities you have now, is it going to precipitate? So all you do here is to say, well, the formula for Q is literally the same as K, which means I take the molarity of Pb 2 plus when not at equilibrium, which are these numbers. We don't know if it's equilibrium, so we plug it in and call it Q. So that means this here, 0.0150 molarity of PbNO3 has the same molarity for Pb. If you're looking for nitrate, it will be double because this is 2 nitrates in here. But we're looking at just Pb, right? So 1 mole of PbNO3 has 1 mole of Pb. So in this case, the molarity is the same. So I can write the same number. Okay. Now for Br, NaBr has 1 mole Na, 1 mole Br. So the molarity for Br will be the same as the molarity of NaBr. So I'll go ahead and write that down also. And then we're going to square that. So let's see what the Q now equals to. Q is 1.84 times 10 to the minus 7. So in this case here, Q is actually smaller than KSP, so no precipitation. So how can you make precipitation happen? Well, you just have to either up this concentration or up that concentration until whatever the product is, it is bigger than KSP. Okay, so sometimes when you do your experiments in our lab here, we had something like this, but it was making PbCl2. So we had to keep adding HCl until you had enough so it will precipitate. So in this case here, it's still not enough. You will not see a precipitation because Q is less than KSP. Let me know if you guys have questions. Okay. So the next thing I want to talk about is something called selective precipitation. It's kind of cool. So are you guys done writing with this? I'm going to go ahead and change to the slides real quick. If you aren't, let me know. I can put it back. So in this case here, if you have different ions around there, you can actually selectively, if you know the KSP and you know what it reacts with, you can precipitate one of them first before the others. Depends on your KSP values. It should be pretty different, so the solubility KSP here makes a difference, right? So a good idea is you can actually separate magnesium and calcium from seawater, okay? So I'm going to go ahead and go to the next question. We want to talk about seawater here, how we want to trigger one ion first out and then the next ion. So here's a sample of seawater. We have some molarity of ions here. I'll write it out. Sample of seawater. So it has ions of magnesium, certain molarity, 0.059. And then you have another calcium ion here, and it's 0.011. So that's your sample. Now, it says here, the Mg2 plus and Ca2 plus ions in seawater can be separated by selective precipitation using, use NaOH, but in this case, you use KOH. The source is that OH here, okay? K is just a spectator ion. So what minimum hydroxide concentration triggers the precipitation of magnesium 2 plus ions. So I'll give you the KSP for these two guys. Since you're talking precipitating with hydroxide, you're going to make the metal hydroxides here. So KSP for the magnesium hydroxide is 2.06 times 10 to the minus 13. KSP for CaOH2 is 4.68 times 10 to the minus 6. See, one is a lot bigger than the other. So calcium here has a lot of ions present. So because they're the same number of ions, there's 1 mole of CaOH2 has 3 moles of ions. Magnesium also has 3 moles of ions. I can directly look at the KSP and kind of, be able to tell you what the solubility looks like. In this case here, there's a lot more ions at equilibrium, so it's more soluble. Mg, on the other hand, is a lot less ions. There's very few ions in there. That means if it's few ions, it's less soluble. Because our equations here are basically the solid, remember? And then you turn it into ions. Okay, so the ion it breaks into is magnesium in this case, and then hydroxide. So because this one here is a lot smaller, this one precipitates first. This one here, because it's a bigger number, it has a lot more ions at equilibrium, it stays soluble. So it doesn't precipitate yet, it stays soluble a longer time compared to Mg. So you can put in some amount of hydroxide and Mg is going to come out first as MgOH2. And then eventually calcium will come out too. Okay, but it will be a lot later. So they're asking you, what's the minimum hydroxide concentration for you to start seeing magnesium hydroxide precipitate out? So basically, you're just kind of like saying Q compared to K. You want the hydroxide to be high enough where it's higher than this number when you put the Q value in, the molarities in, and then it will precipitate. So basically, if you know KSP formula was Mg 2 plus and then OH negative square. We want to set this number to be bigger than 2.06 10 to the minus 13. So I'm just going to write equal here and just know that you want the number to be bigger than that, okay? As long as the OH here, when you solve for that number, you want it to be bigger than the answer, it will cause a precipitation. What's the concentration for magnesium? Well, it's just the concentration from the seawater sample. It's over here. So I'm going to go over and write it in here. So we're basically, it's like Q compared to K here, but we use the K as a line number here. So 0.059 goes in here, and then we are solving for OH. Whatever the OH is, we want it bigger than that number, and then it will cause a precipitation. So OH squared is 2.06 times 10 to the minus 13 divided by 0.059. And then whatever this answer is, we square root it to get hydroxide. And it will be 1.9 times 10 to the minus 6 molarity. So that means when you pour in KOH, as soon as you reach 1.9 times 10 to the minus 6 molarity of KOH or hydroxide here, you'll start seeing magnesium precipitating out. It has to be higher than this number. Magnesium will start precipitating out. So that would be our answer here. The minimum is this. It has to be higher than 1.9 10 to the minus 6. Now, so because of that, we know when OH reaches 1.9 times 10 to the minus 6 magnesium hydroxide begins precipitating. Okay, now if you keep adding it, at some point calcium hydroxide will precipitate too. So it says, as we keep adding hydroxide, calcium 2 plus begins to precipitate as well. But it's going to take a lot more than 1.6 10 to the minus, 1.9 10 to the minus 6. So it says here, once you get that calcium, so at what point, it says, what is the concentration? The question is, what is the concentration of Mg2 plus when Ca2 plus begins to precipitate? So in this case here, they're saying you keep adding hydroxide, calcium will come out. But because the KSP between calcium and magnesium is so different, a lot of the magnesium is going to be gone. It'll precipitate first before calcium will start, just because the difference is big here for the KSP and the solubility. So they're asking you, when calcium starts to come out, how much of the magnesium is still left in the seawater that's not precipitated out, okay? So what you want to do is, number one, find out how much hydroxide when calcium precipitates. So you use the same formula, but in this time you use calcium values for KSP. Once you find that level of hydroxide, take that same hydroxide and plug it back into the magnesium right here, and then we'll solve for the Mg. So we'll say, well, that's the level of Mg that's still there. Okay, so we have two steps here. The first step is I have to use find a hydroxide for when my calcium is coming going to be precipitating. So KSP was written up here, right? And I can write the equation for calcium. It's going to be calcium hydroxide. It's a solid. So remember, when you're writing for KSP, it's always a solid on the left side, and on the right side is the ions. So my KSP is calcium hydroxide squared. And that value of KSP was given in the question. It was 4.68 times 10 to the minus 6. So we'll do the same thing. We find out what the hydroxide is, put the calcium in from the seawater sample. We'll find out how much hydroxide we need for calcium to start precipitating. So let's do that. Calcium was 0.011 from the question. Hydroxide is what we're trying to solve. Equals to the K for KSP for calcium, which is given as 4.68 times 10 to the minus 6. So let's solve for hydroxide. Take a square root of that, you get hydroxide. And that will be 2.06 times 10 to the minus 2. So earlier, as long as you put 1.9 10 to the minus 6 higher than that value, you start precipitating magnesium. See how much hydroxide you need? You need 206 10 to the minus 2 higher than this number before calcium starts coming out. So it's a big difference in molarity for hydroxide. So basically calcium comes out a lot later. So the question here is, when calcium is coming out, how much of the magnesium is left over? So you want to take this number here and plug it back into the magnesium KSP. Okay, so I'm going to write it on the next page. Are you guys ready for me to turn the page? Let me know if you're not, okay? So my OH for that part we found out was, I'll write it again, for calcium to come out. Precipitate is 2.06 times 10 to the minus 2. Okay, that was the value we just got. So you take that and you put it back in the KSP for MgOH2. And it was 2.06 times 10 to the minus 13. And the formula for KSP was magnesium 2 plus hydroxide squared. Okay, now this time here, we're not solving for hydroxide like earlier, we're solving for magnesium. So you take this hydroxide and you put it in here, okay? So then we can look for the magnesium that's left over. So 2.06 times 10 to the minus 13 equals to magnesium, which is what we're looking for. We're trying to find out how much magnesium is left. And the OH is given as 2.06 times 10 to the minus 2. And we want to go ahead and square that. Magnesium 2 plus is 2.06 times 10 to the minus 13 divided by 2.06 times 10 to the minus 2, but you take this and you square it out. And you will get about 4.9 times 10 to the minus 10 molarity. So the fact that the answer is 10 to the minus 10 is a really small molarity. When calcium begins to precipitate, by that time, you only have 10 to the minus 10 of magnesium left over. It started off at like 0.059, which is like 10 to the minus 2. So basically, you remove most of the magnesium already before calcium can start to come out. So they call this selective precipitation, because you can take out one ion a lot faster. And then almost all of the ion is gone before the next calcium ion wants to precipitate. So you basically are cleaning the water from magnesium ion first. Okay, any questions? Everyone good? All right, if you guys don't have questions with the selective precipitation, that part is basically the end of like what I want to call the KSP stuff. I want to go to the KF part next. So on your lecture notes, there's some qualitative analysis stuff I will not be testing you guys on. So this is just basically like if you were in lab, you know, you were mixing like how you can isolate stuff to get certain ions. We're not going to worry about that part. We're going to skip that qualitative analysis and we're going to go to complex ion formation, okay? Like right here. So what in the world are complex ions? So we've seen them in the lab, part B for the lab for last week that was just due, where you were making some cobalt, but it had like charges on it. So here's the complex ion example. So you have a metal ion and you have some like water. It could be a ligand, so they call it ligand because these guys are the molecules or ions that have like lone pairs of electrons. So water does have lone pairs. In the other example, we have chloride ions, and those have lone pairs too. So anything that have lone pairs, the ligands here that can attach to the metal. The metals are ions here, so they form a complex ion. So the water has no charge, but silver has +1 charge. So the overall the ion is a complex ion with a +1 charge. Okay. Now, water isn't. Yeah, it's pretty common. Another common ion, like for example, silver actually prefers ammonia as a ligand compared to water. So if you have water hanging around, you have ammonia here. Ammonia will actually replace the water, and you'll have complex ion of silver and ammonia here. Silver is +1 charge. Ammonia has no charge, so it just kind of hangs out there. If, like, for example, in the lab, we had Cl ion, that's why the cobalt one, I'll just pin some right about here. We had one example, it was COCl4 2 negative, right? Why was it 2 negative? Because there's 4 Cl and each one's -1, and this one's cobalt 2, so overall you get -2 charge. That's why it's -2 here. That's another example of complex ion. So to write a complex ion equation is on the product side is the complex ion, and you take the ions that you use to make it on the reactant side. So cobalt is 2+, and then I have 4 Cl negative. That's how I write the equation. Okay, so complex ion has everybody that's aqueous. When you were talking about KSP, it was just solid going to ions. So the KSP was really easy. It was just always like the product. In this case here, it's going to be more complicated. It's going to be the products over the reactants. Okay, so we will write something called KF. So to do KF here, I'll show you the examples we have. KF here for this guy, if you were to talk about silver and ammonia here as a complex ion, you use 1 silver and 2 ammonia. So the formula would be product, this guy on the top, divided by silver to the power of 1, ammonia to the power of 2. Okay, so same idea like what we learned, products or reactants, just because you're all aqueous, you have more stuff to write now. So what's the difference between KF and KSP? A lot of people get them confused. So remember KSP was just like ion, because the equation is always like a solid going to ion. So the KSP formula is a lot simpler. Okay, you have solid going to ion, and then you have like just a product side on the KSP. Now if you have KF, you have aqueous, aqueous, aqueous. Ions make complex ion, so you have to write everybody in there. So that's the big difference there. KSP was also really, really, really small because they're very not soluble. KF is actually really, really big. So let me see if we can zoom in a little bit. See how the numbers are all like big, none of them are negative? So that's because they're really favorable. If you have the ions floating around and you can make a complex ion, they're definitely going to do it. They're going to favor the complex ion side. Okay, so we're going to do one example of KF calculations, but mainly you want to know how to write the formulas for KF and how it's different from KSP. That's important. A lot of people start mixing them up at this point, so you want to make sure you know the difference, okay? So let's go ahead and write a question here. Remember, KF is big, a lot of ions in there. KSP is small, and only product sites appear on there. So let me go ahead and I'll just start on a new page. Okay. So I'm going to mix two things. 1.5 times 10 to the minus 3 molarity of Cu copper nitrate. So copper 2 nitrate here. We're going to use 200 mils of that. Okay. And then I'm going to use 0.2 molarity of ammonia. I'm using 250 mils of that. So I am doing a lot. This concentration is 10 to the minus 1. This is 10 to the minus 3. So there's a lot more ammonia than I have copper. Nitrate here is going to be a spectator ion because we're actually trying to form a copper and ammonia complex here. Okay, so it says here, after the solution reaches equilibrium, what calcium, I mean not calcium, copper 2 plus remains. Okay, and they'll give you the KF for the thing that you're looking for, which is CuNH3, 4, and 2 plus. So this one is 1.7 times 10 to the, not negative, they're always going to be positive here. This one is 13, 10 to the power 13. So it's a big number. So when they give you this KF here, this is your complex ion that you're trying to make. So you need copper 2 plus, one of them, and you need 4 ammonias to make this complex ion. So this complex ion is my product. So I write CuNH3, 4, 2 plus. So that's my product and it's aqueous. So I know I use 1 copper and I used 4 ammonia. There's no charge for ammonia. Aqueous. Okay, so basically when they give you a KF value, you take this part here and you can break it down to know what ions you use to build it. Your KF formula then is KF is product or reactant, so Cu NH3 4 2 plus, that's to the power of 1, and then you want to divide by Cu2 plus, divide by ammonia. The ammonia is going to be to the power of 4. And that equals to 1.7 times 10 to the power 13, okay? That's one step. And then you do need to do an ice table. So we need an ice table here. And we need to find the molarities for all these guys. So the question here did not tell you the molarity after it's been mixed. They told you this is what they used to mix together. So your total volume is 450, okay? And your molarity times the volume in liters will give you moles of each part, and then you divide by 450 in liters, which is 0.450 liters. Then you can get the molarity. So let's go ahead and calculate the molarity first, okay? So we'll find the molarity of Cu2 plus because we needed an ice table and ammonia. Okay, we gotta find that. So total volume, I'll write it out. Total volume, it was 450, so I'm gonna go ahead and write it as 0.4500 liters. Okay, so I knew it was adding up to 450, so I'm gonna write it down and find the moles first. So the moles of copper 2 plus is take the volume in liters, and then you multiply with the molarity. So 200 mils, it really is 0.2, okay? Liters, and then 1.5 times 10 to the minus 3 moles in 1 liter. So that's how many moles I have of copper. So 3.0 10 to the minus 4 moles of copper. And then to get the molarity, I just take the moles divided by 0.45. So molarity of copper would be 3.0 times 10 to the minus 4 moles of copper divided by 0.45 liters. That will give me 6.7 times 10 to the minus 4 molarity copper. So we'll do the same for ammonia. Find the moles of ammonia and then divide it by 4.45. So the moles of ammonia, you take the, you can see here, it's 250 mils and then 0.2, so 0.2500 liters, 0.2 moles per liter. And you get 0.050 moles of ammonia. It's a lot bigger. So take them to get the molarity. You just take the moles divided by 0.45. So it's 0.05 moles of ammonia divided by 0.4500 liters. And we get here 0.11 molarity of NH3. Okay, so I have the molarities here. I'm going to go ahead and put them in my ice table. So this is my initial value because that's just what I'm mixing together, okay? So my ice table here, I'm going to have copper, and then I'm going to have ammonia, and then I'll have the complex ion. CuNH3, 4, and then 2 plus. So ICE, okay? Now, let's put the molarities in. So in the beginning, it was 6.74 times 10 to the minus 4, and this was 0.11. And this one's 0, because we don't have anything yet. Okay, so, and then from our equation, I'm going to scoot it a little bit here. See how it's 1 to 4 to 1, right? So it's going to go towards the side that's 0. So this is plus x. This is minus 4x. This is minus x. And I do, in this case here, x here is basically going to be almost all of this. So because the complex ion is such a big, K is a big number. You see how big this is? It really, really favors the ion, complex ion part. So all of these guys, the copper will be used because I have excess of ammonia. So this one here, I'll use about all of this, and what I have left over is a very, very small number, okay? I'll call this small number Y, and I'll call my X pretty much as 6.74 times 10 to the minus 4. I'm going to use almost all of my copper because it's my limiting reactant there. Okay, so I'm just going to put that in here. So that's a really small number after I minus X here, which is pretty much almost 6.74 10 to the minus 4. I'll have a little bit Y left over. But this one here, for this purpose, because it's a lot bigger, I'm going to go ahead and minus this number here. So it's 0.11 minus 4 times 6.74 times 10 to the minus 4 here. I'll just put the x in there, okay? And then this one here is pretty much 6.7 times 10 to the minus 4 because it's just x. Then we're looking for this guy. So all we do is we plug it back into the KF, which is given. The KF is given as 1.7 times 10 to the power 13. And the formula was this guy over y and this one to the power 4. Okay, so I'm going to go ahead and write it out. Now, do you agree this number here is so small compared to 0.11? So it's 10 to the minus 4. So by the time you subtract it, it's going to be pretty much just 0.11 here. And we can do it, but it's going to end up about the same number. So I'm going to go ahead and write 6.7 times 10 to the minus 4 up here. And then the copper is Y. And then it's 0.11 minus basically the 4 of the x, right? 6.74 times 10 to the minus 4. By the time you do that, it's still going to be around 0.11. So I'm just going to go ahead and like use 0.11 there instead of the numbers, because it's 0.11, 4 times 6.74, 10 to the minus 4 is like 2.696, 10 to the minus 3, 0.11 minus that is still 0.11 when you round up. So you round, it's still 0.11, okay? So I'm just going to keep 0.11 there. So 1.7 times 10 to the 13 equals to 6.7 times 10 to the minus 4 over y times 0.11, okay? And then we'll solve for y here. To solve for y, you take 6.7, 10 to the minus 4, divide by 0.11, and also divide by 1.7, 10 to the power of 13, okay? Oh, and don't forget we have a power of 4 here, because it's a coefficient of 4 for the ammonia. So I'll write it out. So 6.7 times 10 to the minus 4 divided by 1.7 times 10 to the power of 13 and 0.11 to the power of 4. And that will give me an answer for a small number, 2.7 times 10 to the minus 13 molarity. So basically, very small amount of copper ion will remain because majority of them will be used to make your complex ion here. Okay, so that is the end of our chapter 18 here. And the most important thing is knowing how to write a KF and KSP. I try to not put these complicated questions on the test, but you might see it on your homework, okay? So remember, the y here is a very small number. That's why it's super small here. It's pretty much subtracting almost all of it. And you have very little y left. All right, so if there's no questions.
I have a question.
Uh-huh.
I see like how you got the molarity of the Cu2 plus 6.7. Is that the same like when you go down here in the ice table and it's a 6.74, or like is that different? Because I see sometimes you use the 6.7 and then on the bottom use the 6.74.
I was rounding it, I think, yeah.
Okay, I just want to make sure.
Yeah, let's just use 6.7. I don't know why I wrote 6.74. And then I would change it. We can use just 6.7 because it's like 2 6. I'll cross out all these guys here. Might make it a little simpler.
Okay, thank you.
Cross that one out. Yep. Yeah, because 2 6 is enough here. That was a good question.